In November of 2019, Andrej Karpathy gave a fairly in-depth, if short, presentation at a Pytorch summit. Here's what he had to say. Hey y'all, it's Dr. Know-It-All. While this talk was at a different conference and actually a couple of months before the Scaled ML conference, this video is kind of part 3 of a 3-part series, and this will be the most in-depth and geeky of the 3. If you're not already very familiar with neural network training and such, I highly recommend watching parts 1 and 2, and even my introduction to neural networks, all listed up here. I'll wait till you come back. You go watch those first? Feeling ready to put on your super geek hat? Okay then, let's go. Karpathy starts by going over many of the things we have discussed previously in the other episodes, so I won't go over them in much detail here. Again, check them out if you want to. He goes over smart summon, what autopilot is, how many miles have been driven on autopilot, automatic lane changes, and the fact that Tesla's full self-driving autopilot uses vision, not LiDAR. So you've seen all that before.
Tesla is a fairly vertically integrated company. And that's also true when it comes to the intelligence of the autopilot. So in particular, of course, we build our own cars and we arrange the sensors around the vehicle. But then also we collect all of our data, we label all of the data, we train it on on-premise GPU clusters, and then of course we take it through the entire stack. We run these networks on our own custom hardware that we develop in-house. And then, of course, we are in charge of the full lifecycle of these features. So we deploy them to our fleet of almost 750,000 cars right now. And we look at telemetry and try to improve the feature over time.
First, let's go over the image Dr. Karpathy displayed while talking about Tesla's vertical integration. From the bottom, data comes in. This would be simulation or, more likely now, real-world driving data from the fleet. Though it's a little bit less than clear, it appears that this data is pushed to Tesla's older GPU cluster and their newer and growing Dojo cluster. And you can see my episode on Dojo if you're interested in that. These clusters of hardware use Pytorch's distributed training framework to train the network, and thus, therefore you can see why he's talking about this at the Pytorch Summit, although he really doesn't mention Pytorch all that much in the talk itself. Also recall that training takes about 70,000 GPU hours per cycle, so that's a substantial amount of time to train this model. The trained model is then evaluated in-house. That new model is pushed to the Tesla fleet, either in shadow mode, where it doesn't directly control the car, but guesses what it should do next, or in real-world mode, where it drives the car itself. The telemetry, or data, from the real-world driving is then looped back to the bottom as new data, and the process starts all over again. Let's take a step back for just a moment. What the heck is the Pytorch framework? Pytorch is one of the 2 most popular professional-grade neural network training frameworks available, the other being TensorFlow, which you might have heard of also. There is something of a religious battle between Pytorch and TensorFlow. Both are open source, and they do much the same thing. In fact, I've used both of them myself. But TensorFlow has been adopted a little bit more strongly in professional development environments, while Pytorch is growing stronger in the academic research arena. They both work very well, and both use Python as their main interface. And by the way, if you want a super brief introduction to the Python programming language and/or to Pytorch and TensorFlow, let me know. TensorFlow, however, is maintained primarily through Google. While it's open source, the main distributions come out of Google Alphabet. My thinking on this is that Tesla, as they are direct competitors with Google via their Waymo self-driving platform, don't really want to use Google software if possible. So the decision to use Pytorch instead was probably as much a political one at Tesla as a practical one. The end result of all this is fairly negligible. Pytorch is a great neural network training platform and probably allows a bit more flexibility at Tesla, so it was a very good choice.
So I would like to slightly dive into some of the distributed training that we employ in the team. So the bread and butter for us is, of course, analyzing images. So here's an image. In order to drive in this environment, you actually have to understand a lot about this environment. So perhaps we have to understand the traffic lights, the lane line markings, cars, and so on. So you end up in this very massively multitask setting very quickly, where you just have to know a lot about the scene.
All right, so we've seen this exact image at the other presentation, but now Karpathy is going to get into more detail about how Tesla's Hydronet actually functions, which we'll get into in just a moment. But first, if you enjoy this video, definitely like it so other people can find it, because that's how YouTube's algorithm works, and definitely subscribe if you want to see more of these. Also, a real big shout out to my patrons on Patreon. We have a few new patrons today: Christopher Rubicam, Suresh and Neelam Gajwani, and Fred Clintworth. Hey to everybody, thanks for joining me in 2021. Also, a big thank you to Zenly Music for the intro and conclusion music. He's a great artist. You should definitely check him out on Instagram or YouTube. And also, if you're in the market for a new Tesla, definitely check out our referral link. If you use that, we both get 1,000 free supercharger miles, which is awesome. And finally, a brand new announcement. We are now Amazon affiliates. There is a link in the description. If you just click on that and go shopping, you will help out the channel because anything you purchase in the next several hours, I think it might be up to 24 hours, actually counts, and we get a small commission for that. So that would be great. Thank you so much. And now that your brains had a little bit of a rest, let's take a look at Tesla's Hydronet in more detail.
So a lot of our networks take on this outline here, where you have kind of a shared backbone that has a number of tasks hanging off of it. And just to give you an idea of the workflows and the kinds of networks, these are typically a ResNet 50-like backbones running on roughly 1,000 by 1,000 images, and then they have these heads of these structures that make sense. And of course, we're doing this partly because we can't afford to have neural networks for every single task, because there's many, many tasks, almost 100 tasks. And so we have to amortize some of that computation. So we put them on shared backbones.
Okay, there's a lot to unpack here. First, the text at the left. There are around 4 million input images for the network to process. That alone is mind-numbingly big. The next line talks about ResNet 50. A ResNet 50 model is a very deep neural network that was designed specifically to process and identify images and portions of images. The heads of the Hydra are UNet type models, which are a different flavor of deep neural network model that obviously helps with identification and prediction. And the 15 tasks line means that the shared backbone, the ResNet models, has reduced the 100 or so individual tasks down to about 15 tasks, making the problem more tractable. The image on the right shows how this works in a general sense. The shared backbone takes in raw image data and pre-processes it, dividing image segments into the around 15 prototype tasks. This pre-processed data is then passed on to one of the heads, the UNet model that is trained, say, to identify objects or traffic lights or markings on the road, etc. That's a lot to process, I know. The big takeaway here is that we have a pre-processing neural network that figures out where things are in an image and passes that portion of the image onto another model that is specifically trained to deal with those types of things, like what do I do when a traffic light is red, etc. This is a pretty cool way to reduce the workload from what you might think at first guess would be the easiest method. Have a model start with the raw pictures and find traffic lights and then deal with them, or find lane markings and deal with them, etc. That would be around 100 models trying to work at the same time rather than just over a dozen. By the way, when Karpathy talks about amortization, he just means that they're reducing the processing and memory needs of the system. We've already talked through some of the examples before in previous videos, but let's look at these camera images.
So here's an example of this occupancy grid. We're showing just the road edges and how they get projected. And the car winds its path around this parking lot while the person is summoning it, and it's just trying to find its way towards the goal through this parking lot.
You can see how the car has done the binary segmentation we discussed earlier, marking out the curbs in red. The raw images would be passed to the backbone, which would, along with other things, parse the areas it thought were curbs. That would then be passed on to the what do I do with curbs network that is one of the Hydronet heads. That would then mark out these areas and determine how not to drive over those curbs. Then, of course, as we also discussed last time, we can see the bird's eye view from the stitching procedure done by the bird's eye view network or BevNet. This is critical so that the car can know where it is in 3D space, not just in the original 2D camera views.
But of course, very quickly you run across tasks that actually have to be a function of multiple images at the same time. So for example, if you're trying to estimate depth of any of these images, it might actually be very helpful to have access to the other views of that same scene in order to predict the depth at every individual pixel. Or if you're trying to predict the road layout, or if you're trying to steer the wheel or something like that, you might actually need to borrow features from multiple other Hydronets. So what this looks like is we have all of these different Hydronets for different cameras, but then you might want to pull in some of the features from these Hydronets and go to a second round of processing, optionally recurrent, and actually produce something like a road layout prediction.
All right, I know. So here Karpathy gets really mind-blowing. The Hydronet is not one animal. There are actually 8 of them, one for each camera. And yes, they all have to run at the same time, and sonar and radar is being processed simultaneously as well. So all of these networks talk to each other and over time. I also love how Karpathy says optionally recurrent. That is a sneaky way of talking about what the recently released full self-driving beta has got, temporal continuity of data. Remember, this was a year before that software was released, so Karpathy is being really coy about discussing it. Also, if you want to see an episode on how this works, check out my trajectory prediction episode here. So basically, each camera's network can pass output information or 3D information to the other camera's networks, and they can then collectively produce a master bird's eye view road layout with objects, road markings, etc. on them, as was shown in the Smart Summon video. And all of this can be maintained over time as well by an additional recurrent neural network that is looking back in time for continuity. Note at this point that the network worked very slowly. It was fine for driving like 5 miles an hour in a parking lot, but the frames per second was not adequate for driving at highway speeds.
So this is an example of what a road layout prediction might look like for the autopilot. Here we are plugging in 3 cameras simultaneously into a neural network, and the network's predictions are not anymore in the image space, they are in the top-down space. The stitching up across space and time happens inside the recurrent neural network.
And here we can see a quick example of how this works in a parking lot. I think it's pretty cool that they created and released Smart Summon first. It's like a little practice gym to work on these networks at very low speed before heading to the big time where the car has to drive very quickly with many more obstacles and rules. The last part of this clip refers back to the other talk we discussed, where Karpathy talks about how Software 2.0, which is all neural network based, is eating Software 1.0, which consists of hard-coded C++ rules. This is a big deal that the car is driving in this parking lot not using explicit rules, but rules it devised itself via neural net training.
And then if you've trained recurrent neural networks on videos, you'll quickly kind of notice that these are not trivial training workflows. So as an example, if I want to unroll this graph in time and backpropagate through time, maybe we have 8 cameras, we unroll for 16 time steps, we use a batch size of, say, 32, then we are going to be holding in memory 4,096 images and all of their activations in a single forward pass. So very quickly, your typical distributed data parallel will break because you can't hold this amount of memory, this amount of activations in memory of a single GPU or even a single node.
So let's take a look at this image. The text is the most important part, as the picture just shows the 8 camera networks feeding into the central processing network that ultimately makes the predictions. In the first line of text, we have 8 cameras, which is obvious. 16 time steps is probably about 1 second of time. The network seems to run at about 17 frames per second, so this is more or less 1 second of video data. And the batch size is 32. What does this mean? Well, the best way to train a neural network is not to train on one image at a time, but to suck in a bunch of them at once and train on them all at once. The reason for this is a little bit subtle, but in essence and by experimentation, it's been shown that training on a chunk of data that is larger helps to smooth out any bizarre changes one image might cause to the network. For batch size, generally the more the better. The limitation is memory. 32 images in a batch requires 32 times more memory for the network to process. 32 in general is a pretty nice batch size, so this is kind of a common number that people often use. The second text line shows that with all of these parameters, by simple multiplication, you get 4,096 images in a forward training step. Yikes. And remember, each image is something like 1280 by 720 or 720p resolution. So that is 3,774,873,600 inputs into the neural network. That, my friends, is a big number. By the way, note, each image is not an input to the network. Each pixel is an input. And actually the number is probably 3 times this size, as there are 3 color channels too. So that's around 10 billion inputs if they're actually using color for their data. So this is why the red line at the end says requires a combination of data parallel and model parallel training. They have to split up all of the images and tasks into parallel steps that happen at the same time. No system has enough memory or processing power to deal with all of it at once. With, by the way, the possible exception of the new Dojo trainer they are building. But as the exact specs are not public yet, it's hard to know if that is true. But it would surely speed things up if it could handle this much input data and models this big.
It also gets kind of tricky in terms of training these networks because the typical simplest case might be a round-robin training of different tasks. So you're training task 1, then all the workers in the pool are training task 1, then task 2, 3, etc. That gets out of hand when you have 100 tasks. So instead, what might make sense is to actually have a pool of tasks. And some of the tasks are doing objects. Some of the tasks are doing road layout. Some of the workers might be doing depth, and so on. And these are all very heterogeneous workflows, but they coexist, and they're training different pieces of the network at the same time. And then you can arrange them in synchronous, asynchronous way, or play with this to really squeeze out all the juice out of it.
Here, Karpathy discusses the ins and outs of how to actually train all of these heterogeneous networks. It's not exactly clear, but what I believe he's implying here is that if you only train one task first, like how to recognize stop signs and what to do with them, the system will overfit or overtrain to that data. Then when it goes on to the next training task, like recognizing construction cones on the road or something, it will be too specific to stop signs to do a good job on traffic cones. So instead, you have to kind of interleave training stop signs and traffic cones at the same time, plus all of the 100 other tasks that need training at the same time. So honestly, just coming up with a good way to train this behemoth must take a huge amount of time and effort.
And then you're not just training this once, you have to iterate on this. So of course, there are researchers and engineers in a team that actually have to improve on this. And so as you can imagine, we do a lot of neural network training at scale to get this to actually work. And then we are automating a lot of the workflows. It's not just about the neural network training itself, but everything surrounding that. So in particular, we have to calibrate all the different thresholds. We have a process for that. We have a lot of in-the-loop firmware in-the-loop validation, other type of validation and evaluation to make sure that none of these 1,000 different predictions that we make can regress, and so on.
Note again from this that it takes about 70,000 GPU hours to do one training set. So a massive compute cluster is needed to do this training in a reasonable amount of time. And as Dr. Karpathy notes, no particular network like stop signs can ever regress or get worse, or that would be super dangerous. So there's a ton of validation and evaluation that is needed at each step. And of course, if things don't work well, you have to correct and go back and train all 70,000 GPU hours over again.
I would like to also talk a little bit about the inference aspect of this, because I talked quite a bit about training. As I mentioned, we have sort of our own backend that our hardware team has developed. We call this the FSD computer. It offers about 144 int8 teraops of capability. Compared to the GPUs that we were using before we introduced this chip, this is roughly an order of magnitude improvement with lower cost. So we use this in all the latest cars that are now coming out of the production line, and we target all of the neural networks to these chips.
I have to say, I love this image and what it means. First, the left image shows that there are two of the main chips on board the full self-driving computer. I'm going to do a whole episode on embedded chips and redundancy very soon, so I'll table that discussion for now. Definitely subscribe if you want to see that one. Within each chip is the center image. There's a CPU, in fact, a bunch of them on the right, a GPU at the top, and most interestingly, two NPUs or neural processing units at the bottom. These are specialized GPUs designed for neural network processing and training. You can see my neural processing unit video for more information on this. Also note that each chip has 6 billion transistors on it at a 14 nanometer processing size. And finally, at the right is one NPU diagrammed. The really cool part of this image is that it shows the NPUs have onboard memory that allows them to load in data and process them all on board without having to pass data back and forth to very slow external RAM. This is an exquisitely designed, purpose-built chip, and I cannot wait to talk about it more soon. Finally, note that the whole package runs on less energy than an old incandescent light bulb, sub 100 watts. This is a huge deal for a battery car. You can't have the car's battery dying off simply from the computer running rather than driving the car around. So this system is beautifully designed, very fast, and low power. That's some nice hardware.
And Dojo is a neural network training computer and a chip. And so we hope to do the exact same thing for training as we did for inference, improve basically the efficiency by roughly an order of magnitude at a lower cost. But I'm not ready to talk about more details on that project just yet.
And finally, Dojo. So this brief finale to Karpathy's talk gets into the hardware aspect of Dojo, which is still a bit of a mystery today. But in general, they're building out a more beastly version of their full self-driving inference chips that are used in all our Teslas to do the training itself. This will allow the team to train on the same hardware stack more or less as they drive the cars on, which is more efficient as a methodology. But also, since the hardware is optimized just for neural net training, it's designed to do this work extremely rapidly and efficiently. What are my thoughts on all this? The task Karpathy et al. Have set out for themselves is insanely large. Remember, we sent men to the moon over 50 years ago, and cars still don't drive themselves. That's how complex this task is. But we are getting closer and closer, and as these gory details show, it's not just the raw processing power of our chips that are making this possible now, it's the incredible minds coming up with novel ways to solve extremely complex problems that are making this possible as well. What can one say but congratulations to Dr. Karpathy and his whole team. All right, I hope you found this very detailed episode informative and fun. If you did, definitely remember to like and subscribe so other people can find it. And also definitely remember to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.